So in the last lesson, we went over the fact that derivatives are the limit of rise over run, and that you could find a formula for the derivative of a particular function by taking that limit. But really, when we're using calculus, we don't take limits every time. People did that already. We know the answers for that. So rather, we use a set of rules for derivatives that are derived from that process. And so what I'm going to do in this video and the next couple of them is go over some of those rules. Okay, so in this video, we're going to go over some basics and then some algebraic rules. Okay, so just some basics here. These are building block type basics, the first two. One is that the derivative of a constant function, k, is 0. Okay, what does that mean? If we have a function where f of x is k, same value for all values of x, it has a slope of 0. We don't need calculus to tell us that, but having it down as a rule gives us a building block that we can use in conjunction with other rules. Okay, so that's one. Next rule is if we have taking the derivative of a constant times a function of x, okay, what that is that constant times the derivative, okay? So last time we learned how to take the derivative of x squared. We took that as the limit of a difference quotient. If we want to take the derivative of 5x squared, what this is telling us is that we take the derivative of 2x. Remind ourselves that that is x squared, and we multiply it by that same constant. So the way I got this derivative of 10x is that it's 5 times 2 of 2 times x, and this is my k here, and this is the derivative with respect to x of x squared. So that's nice. We can just kind of factor out those constants. All right. The final basic rule is, in one sense it's basic, and in another sense it's super duper empowering, and it is the power rule. Okay, so again, in unit 4, we took the limit of the difference quotient for y equals x squared to find out that that derivative was 2x. Well, there's lots and lots of powers of x that we might be interested in the derivatives of, and the power function, the power rule tells us how to take the derivative of any function involving a power of x. Okay, so the derivative with respect to x of x to the power n is n times x to the n minus 1 power. Okay, so people often think of this just kind of as a mnemonic, that you're kind of bringing down the exponent, multiplying x by it, and then subtracting 1 there. Okay? And indeed, when we took the derivative of x squared, we do indeed bring down the 2 times x to the power 1, which is just the 2x that we had. Okay, so looking at somewhat higher power of x, if we want to start off with f of x is x to the 5th power, we take its first derivative, it's 5, bringing down that exponent, times x to the 4th power. So the powers of x get lower as we take derivatives. Okay, so now I want to do something that's a little bit of a preview of where we're going to end up in a couple lessons, where we're going to end up at the end of Unit 5. So stepping out for a minute, I took a derivative of this function. I used the power rule, lovely. I got the derivative, which is itself a function of x, okay, and we're expecting that. That's the whole point with nonlinear functions, that the slope depends on where we are in terms of values of x, so it itself should be a function of x. So this derivative is a function of x. We can take its derivative, and that's what I'm going to do, okay? So what I'm going to say is, let's take the derivative of the derivative of x, and we would call that the second derivative. It's the derivative of the first derivative of prime of x. And we could do that because f prime of x is just a function. Okay, so I'm saying we could do it. Let's do it. So I'm going to combine the power rule now with that constant multiplication rule. My constant of 5 is just out there multiplying the derivative of x to the fourth, and that is 4 times x cubed. So we get 20 x cubed. And I can just keep going. I can keep taking higher and higher derivatives I want. I can take a third derivative. Okay, it's my 20 constant there, multiplied by the derivative of x to the third power. That is 3, multiplying it times x squared. I get 60 x squared. At some point, I get tired of using these little hash marks here, so let's start noting derivatives like this. It's a parentheses with 4 there. The fourth derivative of x is 60 times 2x, 120x. Okay, let's just keep going. Let's keep going. A couple more derivatives here. The fifth derivative of x. Well, now we're at a point where the fourth derivative was a linear function, so the fifth derivative is just 120, and by the sixth derivative, we're taking the derivative of a constant function. We get down to 0. So a couple of things I want to say. First of all, how often in real life do you ever want to take 6 derivatives of a function? Never is probably the answer there. It's just kind of an exercise here to help us wrap our brains around the concept. In general, we're very interested in the first 2 derivatives of nonlinear functions. Sometimes, some unusual cases, yeah, maybe we might be interested in the third derivative, but these really higher order derivatives, really pretty rare. Okay. Other thing just to note about this is when we're taking derivatives of powers of x, we're getting lower and lower powers. That's part of the power rule, right? We're decrementing the exponent every time we take a derivative until at some point we get to 0. Another point just to notice here is that the power rule encompasses the derivative of a linear function and the derivative of a constant. If we wanted to, instead of thinking about those as separate cases, if we just wanted to think about this as the derivative with respect to x of 120 x to the first power, we would indeed get 120 times 1 times x to the 0 power, which is 1, which is 120. Okay. So power rule, really great. Now we can differentiate all those powers, and when we add in the constant multiplication rule, we can take more derivatives than anybody ever really needs to take. 2 other comments on the power rule. One is that it works for negative exponents too. Okay, so let's say we had f of x is 1 over x. Okay, and we might remember that we could rewrite that as x to the power -1. That's what the negative exponents do, is they're putting the powers of x in the denominator of a fraction. So we're just going to apply that power rule. We're going to say that f prime of x is bring down the exponent, the -1, times x to the -1 minus 1 power. So here's where you do have to be a little tricky managing those negative numbers. This is still our n minus 1 here, and this is our n from the power rule. Okay. putting that up a little bit, it's negative x to the negative 2 power. We might want to rewrite that as negative 1 over x squared. You can write it either way. Okay. Take one more derivative here. So second derivative of the function we started with. So again, as we're taking these successive derivatives, we want to be able to keep straight that we've got what's sometimes called a primitive function, the function we're starting with, the first derivative that tells us how the primitive function changes as x changes, the second derivative, which tells us how the slope of the primitive function changes as x changes. That second derivative here, the easiest way for me to apply the power rule is to look at the function, the first derivative written this way. Okay? So it's my negative 1 times negative 2 times x to the negative 2 minus 1 power. Okay, so again, thinking about where the power rule components are, this was just a constant, this negative 1, multiplying x to the negative 2 power. The negative 2 is my n in the thing whose derivative I was taking here, and this is my n minus 1. And sorting out all the negative signs here. So the negative 1 times the negative 2 on the constants, that gives me a positive 2. Where'd my pen go? Positive 2 there in the numerator. And then in the denominator, I've got x to the negative 3 power. So x cubed. Okay. So in one sense, the power rule applies just as easily to negative exponents as it does to positive exponents, but there is that kind of tricky issue that you have to manage those negative signs. And another great thing about the power rule here, power rule applies to fractional exponents. Okay. So let's see, say we have f of x is x to the 1/2 power. Okay, so that is a function because when we write x to the 1/2 power, the function indicated there is the positive square root of x. Okay, that's generally what we mean by fractional exponents, is the positive root that the fraction is indicating there. So just applying that same rule. My n now is 1/2, so it's 1/2 times x to the n minus 1 power. Well, 1/2 minus 1 is negative 1/2. Okay. And again, I might want to write that as 1 over 2 x to the 1/2 power. I might want to, but honestly, if I was going to take another derivative, which guess what I am, maybe it's just easier to look at it that way. So taking one more derivative there. The second derivative, I've got my constant 1/2, so let's just keep that. My n now is negative 1/2, so I'm bringing that down, times x to the n minus 1 power. So negative 1/2 minus 1 is x to the negative 3/2 power. Okay, that's my second derivative. Again, kind of making it look a little bit simpler, would give me negative 1 over 4 x to the 3/2 power. Okay. So those basic rules actually give us quite a lot. And I'm going to add 3 algebraic rules to this, which is going to allow us to take expressions term by term, take the derivatives term by term. All right, so let's do that. Algebraic rules. Okay, first one, addition rule. For all of these, we're going to be kind of thinking of two functions here. So we're going to have u be a function of x, u of x, and v is also a function of x. Okay, so I'll use both, I'm going to use the same letter to denote the name of the function and the name of the variable that the function assigns a value to. So rather than having y and f here, u is playing the same role. Addition rule is great. It says that the derivative of a sum, u plus v, is the sum of the derivatives. There, isn't that good? Okay. So that's going to let us take the derivative of a lot of polynomials. If we want to have the derivative with respect to x of 4x to the 5th power minus x squared, what this says is I can take the derivative of my u, 4x to the 5th, add it to my derivative of v, negative x squared. That's the derivative of the whole expression. So just really nice and seamless, just how you'd like it to be. So that derivative would be 20x to the 4th minus 2x. Okay. Isn't that great? Wouldn't it be great if the same thing were true for products and quotients? It would be great, but that's not how it is. All right, the product rule is not so simple. Not terrible, I don't want to make it sound harder than it is, but it is not true that the derivative of product is the product of the derivatives. Sorry. Rather, if we have the derivative of the product of u times v, what it is it's v times du dx plus u times dv dx. Okay, so we've got these two functions we're multiplying together to make kind of a compound function here. And we want to take the derivative of that product function. It's the second term in the product times the derivative of the first plus the first term in the product times the derivative of the second. Of course, because it's a sum, you could also say that it's u dv plus v du. You can write it either way here, but it's still a little bit trickier to manage than just taking the derivatives and multiplying. Yeah. Okay, so if we have something like some product here, so x squared plus 7 times 2x minus 5, I'm going to take that derivative. Here's my u, here's my v. So the product rule says take v, multiply it by the derivative of u, take u, and then add to it u multiplied by the derivative of v here. So it's 2x minus 5, just copying my v term, times the derivative of u. So the derivative of u, the derivative of x squared plus 7 is 2x, plus my u term, x squared plus 7, multiplied by the derivative of v, which is 2. So that's the derivative. I could multiply it out in combined terms if I really cared about it, but I think I'll let you do that if you want a little practice with simplifying long expressions. So if products are tricky, you're probably guessing that quotients are too, and you're right about that. If we have the derivative with respect to x of u divided by v, what that is v times du dx minus u times dv dx divided by v squared. Yeah. Again, don't make more of it than it is. It's not that hard to just sort of fill in the blanks. And let's just do an example right now. The derivative with respect to x of 5x squared plus 13 divided by 3x cubed plus 2x squared. So my u is up here, 5x squared plus 13. My v is 3x cubed plus 2x squared. So that derivative has v squared in the bottom. So in the bottom we have 3x cubed plus 2x squared, the whole thing squared. And in the top we have v, so let's just copy v again here. That's 2x squared times the derivative of u, so the derivative of the top, the derivative of 5x squared plus 13, that is 10x. And we're subtracting from that u, so the thing I just took the derivative of, 5x squared plus 13, times the derivative of v. So that would be 9x squared plus 4x. All right. Again, not super fun, but let me make a couple of observations about the quotient rule that will kind of help you use it when you have to. First of all, unlike the product rule where it doesn't matter whether you first take the second term and multiply by the derivative of the first and then add to that the first term times the derivative of the second, or do it the other way around, it's fine, okay, because you're adding them together. You can do u times dv dx plus v times du dx, or you can do it the other way, no big deal. But for the quotient rule, because what we have is a difference here, you do have to get it in the right order. The way I remember that is, you saw me do it when I did this little example. I write the denominator first, and then I just remember that the very first thing that I'm going to write in the numerator is the same thing. Okay, so I've got v all over the place here. I've got v here and v there. So I've written v twice. Again, just helps me remember. The other thing about that, so let's kind of drop back and think about, well, what are we doing when we're taking derivatives? We're trying to find slopes, and what is the information we're trying to get from finding the slope of a function? Often we're wondering, is this function increasing or decreasing? And for the case of a derivative we get through the quotient rule, what I want you to notice is we have a square term in the denominator. So if we're interested in the sign of this derivative, we don't need to worry about the denominator. So managing that whole business of like it being a fraction is no big deal. Okay, so the sign of the derivative of the quotient here is the same as the sign of just the numerator. So if I'm going to try to figure out when this thing is positive and when it's negative, I just have to look at the numerator. The final thing you might want to be thinking here is, well, I'm not too enthused about taking derivatives of products and quotients. So thing one, it's not that bad. It's a little bit of algebra. You'll do some problems and see that it's not that terrible. But thing two, it could get bad fast. Like once you start having lots of terms multiplied together, that can get really tedious. And so you'll see as we go along, sometimes we'll try to find ways to take products and quotients and turn them into sums and differences if we want to take their derivatives. Okay, and I'll just give away the secret right now. A great thing for doing that is to take the log. A property of logs, that the log of a product is the sum of the logs, turns out to be our friend if we have to differentiate products with lots of terms. That's getting ahead of things, though. We've got a couple more quasi-basic, intermediate level rules to go over. And so that's what we're going in the next video.